So we've talked about how we add together vectors graphically, that we draw them tail to tip, one after another, and then we draw in the resultant vector from the tail of our first vector to the tip of the last vector. Well, how do we add together algebraically? Usually what we're going to want to do is not just be able to diagram what's going on in the problem, but we're going to want to calculate what's going on. And so we need to know how to add vectors together algebraically to do that. Well, let's start actually by doing what we know to do graphically. So again, here I've got three vectors A, B, and C. They're all drawn from the same origin. Each of them makes an angle with the x-axis. And so all I'm going to do is start by redrawing those three vectors to show the vector addition problem. So I'll draw A, then B, then C. And now the resultant vector is the vector that runs from the tail of A to the tip of C. Well, I can think about each of these vectors in terms of their components. So if for vector A, it has an x component that points to the right, a y component that points up. B has an x component that points to the right and a y component that points down. C has an x component that points back to the left and a y component that points down. And then the resultant vector, again thinking about it in terms of its components, it has an x component that points to the right and a y component that points down. So the interesting thing is that algebraically, what this graphical representation is showing me is it's giving me the rules that we're going to use algebraically. So if I think just about what's going on with the x components, what I notice is vector A takes us a certain distance to the right. B takes us further out to the right. Then C, because it's a negative x component for vector C, C brings us back to the left. But you can see that if I take the x component of vector A plus the x component of vector B plus the x component of vector C, I end up with the x component of the resultant. We can do the same thing with the y components. And again, what you'll notice is I go up a little bit for A, then I come down for B, come down even further for C. Just like with the x components, what I get is that when I add up my positive y component for A plus the negative y component of B plus the negative y component of C, I end up with the y component of vector R, which in this case also happens to be negative. So what this means is our vector equation here, A plus B plus C equals R, what this vector notation is really hiding is a set of component equations. So this is sort of a shorthand way of writing this equation, A plus B plus C equals R, for each component that we need in the problem. So here we happen to have two-dimensional vectors, right? They're vectors that point in both the x and y direction, so we need two component equations. If we had vectors that lay entirely along the x-axis, we would only need one equation. It would happen to be the x component equation. If we had vectors that lay entirely along the y-axis, again, we'd still only need one equation. This time it would just happen to be the y equation. So for this class, again, because we're going to sort of limit ourselves to talking about vector problems that tend to be two-dimensional, we're going to tend to just set up two component equations, x and y. But many of you will go on to take classes where, of course, you'll deal with three-dimensional vectors. And there, this vector equation, A plus B plus C equals R, you would have three component equations, one for x, one for y, one for z. So let's look at an example here. So in terms of adding vectors algebraically, here we're told we have three vectors that lie in the xy plane. Vector A has a magnitude of 12 meters and points in positive x. Vector B has a magnitude of 15 meters and points in negative y. Vector C also has a magnitude of 15 meters and points in the direction 36.9 degrees above the negative x-axis. We want to know what are the x and y components of the resultant vector that we get when we add A plus B plus C. So how are we going to do this? Well, the first thing we're going to do is draw the vector diagrams. And so in this case, we're given information so that we can draw all the vectors from the same origin. So that's where we'll start. So let me draw out my x and y axis. I'm told that vector A lies along the positive x axis. Vector B points in the negative y. Vector C makes a 36.9 degree angle with the negative x-axis. It's above the negative x-axis, so there's vector C. So there's the first step. I'm going to draw in the vector diagram, And in this case, the vector diagram I'm going to start with is the one that shows all the vectors drawn from the origin, because that's simply the way that I was given the information in the problem. Now I'll come back and draw in the vector addition diagram. So draw them in tail to tip, which is going to let me see the resultant vector. So just in doing a relatively rough sketch here, before I do anything, what I'm going to recognize is, well, I expect the y component to be negative, and I expect the x component to be pretty small, right? Unless I really go through and do a scale diagram, I don't want to read too much into what's going on with vector r. But here I've been pretty consistent about keeping the magnitudes of my vectors constant as I redraw this diagram, and so I've got a pretty good sense that the y component of vector r is going to be negative and the x component is going to be something pretty close to 0. So there's step 1. Draw my two vector diagrams. Step 2, pick a coordinate system. Well, in this case, I basically have already done that because I was given the information on these vectors relative to the x and y coordinate plane. So I've already laid in the x and y coordinate system. Step 3, I need to determine the x and y components for each vector. Well, let's start with vector A. I'm told it has a magnitude of 12 meters, and I'm told it points in the positive x direction. So what I know is that the y component of vector A has to be 0 because vector A lies along the x-axis. All of its magnitude has to be in the x component, and in this case, because it points in positive x, that component, the x component, is also positive. For vector B, it has a magnitude of 15 meters, and its direction is in the negative y. So again, because I know it lies along the y-axis, this means I know that the x component of vector B has to be 0. The y component is the entire length of vector B, so the full 15 meters of magnitude, and it points in the negative direction, so it must have a negative component. Vector C, of course, doesn't lie along one of my axes, so A and B both lay along an axis. Vector C doesn't, which means it's going to have two non-zero components. So of course, when I break it up, what I notice is the x component is going to be negative, the y component is going to be positive. I've got a 36.9 degree angle that the vector makes with the x-axis, so cosine of that angle is going to go with the x component, sine of that angle is going to go with the y component. And so I have an x component for vector C of negative 15 cosine theta, where theta is my 36.9 degree angle, and a y component of plus 15 sine theta. Now, one of the things that we're typically going to do with these problems is organize this information in a table. We don't have to, but one of the things that's really nice about this table is it gives us an easy way to check and make sure that we aren't making mistakes before we go further in the problem. So it's easy enough to check and make sure, are our zeros in the right place? So is it correct that the y component of vector A is 0? Yes, because it lies along the x-axis. Is it correct that the x component of vector B is 0? Yes, because vector B lies along the y-axis. Have I got the signs right? So does the x component of vector A point in the positive direction? Does the y component of vector B point in the negative direction? For vector C, is its x component negative, its y component positive? Have I got the right trig functions? So the table just makes it easy to check all these things and make sure that we don't have any mistakes that we've sort of already embedded in the problem before we worry about going any further with the algebra. And then what we'll do here in this case is the resultant vector I don't actually know anything about. And so what we'll see is if we don't know anything about a vector, the easiest thing to do is simply to leave it in its components. So what I've chosen to do here is simply let vector r be, well, its x component I'm just going to leave as the x component of vector r, and its y component I'm going to leave as the y component of vector r. So it's not the only way to deal with this, but it tends to be the easiest way to deal with a vector where we don't know anything about either its magnitude or its direction. So now, next step 4, is I can go through and set up my equations. With the table, basically what I'm doing is I'm setting up the x and y equations in each column. So notice that that's the x component of vector A, that's the x component of vector B, that's the x component of vector C, and my x component equation says I just want to add those three things together. That has to equals, that's what this double line is representing, it's basically the equal sign in my equation, so that has to equal the x component of vector r. So all I need to do now is basically go down my table, write 12 plus 0 plus negative 15 cosine theta equals the x component of vector r. I can set up my y component equation in exactly the same way. So here, again, I've got my y column, and I'm going to add together the y component of vector A, which is 0, plus the y component of vector B, which is negative 15, plus the y component of vector C, which is 15 sine theta, and that has to equal the y component of vector R. So I can use my table to set up my two equations. So I have an x component equation and a y component equation because I'm adding together vectors that lie in two dimensions. Step 5 then is solve for the unknown. So the first thing I want to do at this point is stop and check and see what my unknowns are. So if I want to be able to solve this and I only have two equations, that means I can only have two unknowns. And in this case, it's relatively easy to recognize that the unknowns happen to be the x and y components of vector r. So sure enough, I have two unknowns to go with my two equations. Each unknown has its own equation, which algebraically makes this pretty simple to deal with. And so now I can go through and use my x component equation to solve for the x component of vector r. In this case, when I plug in my cosine of 36.9 degrees, multiply that by 15, that happens to be 12, so 12 minus 12 is just another way of saying 0 meters. I can use my y component equation to solve for the y component of vector r, and again when I plug in my values I end up getting that the y component of vector r is negative 6 meters. So in general, we're going to go through this process every time when we're doing a vector addition problem. So we're going to draw ourselves a couple of vector diagrams, one showing the vectors from the same origin, one showing the vector addition, and letting us see the resultant. And again, which one of those we draw first is really just going to depend on the information that we're given in the problem. We're going to pick a coordinate system, if we haven't already, in terms of putting together that diagram. We're going to break our vectors up into components using that coordinate system. We're going to set up the equations that we then need. We'll have one equation per dimension within the problem, and then we'll solve for the unknowns. And again, if we've done this right, we'll have one unknown. We'll have the same number of unknowns as we have number of equations. Now I can go the additional step and ask for the magnitude and direction of the resultant. So instead of asking for the components of the resultant vector, if I were to ask to find the magnitude and direction of the resultant vector, that would say, well, tell me about r, not just in terms of its components. And I know that to get the magnitude of a vector where I know its components, I just need to Pythagorize. So since I've already in step 5 solved for what the components of vector r are, I can go ahead and take advantage of that. Square root of x component squared plus y component squared. So 0 squared plus negative 6 squared, take the square root, that's just 6 meters. Step 7, if I also want the direction, I might need to use the inverse tangent to find the direction. But in this case, what I'll notice is the inverse tangent here isn't really what I need. I just need to recognize that this points in the negative y direction. So if vector r had two non-zero components, I would use the inverse tangent. But because one of its components is 0, I know it lies along one of my coordinate axes, and so it's easiest to just explain that in terms of which direction that it points relative to x or y.